very happy and delighted to share that we have successfully developed our first working supercapacitor model from our research laboratory at RV College of Engineering, Bangalore, India. This working prototype supercapacitor model consists of transient metal characterisation based material. This is exhibiting very good chronopotentiometry and cyclic potentiometry results. Based on that, we have designed a coin cell and tested for supercapacitor applications. Here is a demo video of our first working prototype supercapacitor.
Why is this work so important? Supercapacitors find applications in hybrid vehicles, electric mobility, fast charging stations for e-vehicles, high-speed trains, aerospace and defense, offshore wind structures, electronic devices, and many. According to precedence research, the global supercapacitor market size value was valued $5 billion in 2021, and it is expected to hit $25 billion by 2030, growing at a CAGR of 23.5% from the year 2022 to 2030.
So let us explain how we made our first working prototype supercapacitor, starting from synthesizing nanomaterials to developing a prototype device.
We have synthesized transition metal chalcodonide based nanomaterials for our supercapacitor applications. The stoichiometric amounts of transition metal salts dissolved in required amount of distilled water along with chalcodonide source are kept in Teflon tubes which are placed in the autoclave and which are done hydrothermal treatment for 180 degrees Celsius for 2 hours. After the hydrothermal process, we have kept our product for cooling until room temperature. After that, this is the color which we got our product as. We need to wash this to remove the impurities in it. So we have used this centrifuge process to remove it. We are keeping this we will wash it with 2 times water and then 1 time acetone. We will close it, then we will set the required amount of RPM and then it will run. After centrifuging process, the clean product is transferred into this petri dish. This petri dish is kept into that oven at 80 degrees Celsius for 30 minutes for drying. The dried product is taken out and then the product is tested for its crystallinity, purity and morphology using tests like XRD, SEM, Raman and other characterizations. After the characterization, the nanomaterial is used to make a working electrode for testing of supercapacitor applications.
Once we have synthesized the nanomaterial, we use it as a working electrode. So we put that working electrode in a mortar, then we add PVDF and NMP. Once the slurry is prepared, we remove that material and we paste it on a Torre carbon sheet. Once that material is pasted on Torre carbon sheet, it is then kept for drying at 80 degrees Celsius for 2 hours. Once it's dried, we use that as a working electrode to check cyclic voltammetry and chronopotentiometry supercapacitor application.
The nanomaterials which were synthesized has been loaded on the Torre carbon sheet, which acts as a working electrode. So the slurry of nanomaterial along with the binder has been loaded on the electrode on the Torre carbon sheet. The same Torre carbon sheet is used here with the green lead, which is a working electrode, and with the white lead we have connected a reference electrode, which is a saturated calomel electrode, and the red lead, which is a counter electrode, which is a platinum wire which acts as a counter electrode. So using electrochemical workstation, we will be studying the electrochemical properties of a given nanomaterial. After connecting the working electrode to the electrochemical workstation with the 3 leads, we have studied the electrochemical properties of this material. The first property which we have studied is cyclic voltammetry, and secondly chronopotentiometry, and thirdly the AC impedance studies. All the 3 studies were done. So the property showed very good electrochemical property. Hence we are going to have a supercapacitor device using the material.
After preparation of nanomaterials, we are going to further proceed with preparation of electrode. This is This is our nanomaterial which we have synthesized in our laboratory, which is a very good promising material for supercapacitor application. So for preparation of electrode, we need carbon sheet, we need PVDF which is a binder, we need NMP which is a solvent. All together are then mixed in a mortar and made a slurry to paste it on a working electrode. So these are the working electrodes which we have prepared by applying the slurry on a carbon sheet and then dried, which will then act as a working electrode for supercapacitor coin cells.
So now, as we have seen that the nanomaterial is suitable for supercapacitor application, we shall see how to make a coin cell. So first we shall place a positive electrode on the positive side of the coin cell cover. Then we shall place a separator. We shall adjust it so that it comes to the center of it. Then we shall place the negative electrode. We have dipped this in the electrolyte so that it gets wet properly, and then we shall also add some electrolyte in this after placing the metal plate. So I have electrolyte in the syringe, so let me put it here. After that, I'll place a wave spring which helps in maintaining the electrodes intact. After placing everything, there comes the negative cover. Now we shall crimp it. So this is the assembled coin cell. Now we shall crimp it. We close it first and then we shall apply a pressure of 80 bar. After applying, we just leave it so that it reaches back to 0, and then we open it. Now we'll slowly open it. And we have a coin cell crimped ready. This is the crimp.
Once the coin cells are crimped, we have tested it for GCD and cyclic voltammetry. Once that is done, we are using this coin cell to glow a LED. The LEDs are connected in series and also the coin cells are connected in series. The coin cell is charged using this electrochemical workstation, and here is the demonstration video.
Congratulations to the students for successfully developing the working prototype of a supercapacitor as a part of their UG major project. We are very much thankful to Professor and Dr. Krishna, HOD of Mechanical Engineering, and Dr. Sudha Kamath, HOD of Physics, and Dr. Raviraj Kasnur, HOD of Chemistry Department, for their constant support and encouragement throughout this product development.
Hearty congratulations to the entire team who have successfully developed a first prototype, an asymmetric supercapacitor from our research laboratory at RV College of Engineering, Bengaluru, India. We thank our SST, our principal, all the faculty and staff and students for their encouragement and continuous support.
So we are also happy to provide consultancy services, especially in making nanomaterials and also for the fabrication of working prototype supercapacitors, and we are also willing to have meaningful collaboration.